Hello, hi everyone, welcome back to the channel. So in this series of binary search, this is going to be the very first video where we'll be learning about the concept of binary search and how can we apply them in problems. What are the problems which we can solve using this algorithms? Let's start with the very basic definition of binary search. So what is binary search? As it is clear that it is used for searching something. So if let's say we are given a sequence of integers, they are sorted in ascending order or descending order. So in this example, the sequence is sorted in ascending order. So we must have a sorted sequence. And we want to search for a target element in this sequence. We can use binary search to search for the target. And this is counted as an efficient searching algorithm. How does it work? Let's see that. So in this sequence, we pick the middle element. So for this sequence, the middle element is 6, this one, at index number 3. Now compare this middle element with the target. We see that the target is greater than the middle element. That means the target, if exists in the sequence, must lie in this range. And this entire space is discarded. Fine. Obviously, the target, which is 10 greater than 6, will not lie to the left of the array, to the left of this middle element. It must lie to the right of it. So this is the new search space. So initially the search space was the entire array. Now the search space reduces to this, from 4 to 6. Again pick the middle element. The middle element for this new search space would be this, that is 10. Now compare the middle element with the target and it matches. That means I have found my target at index number 5. So 5 is the answer. So how does it counted as efficient search? Because let's say we perform linear search over the array, then we have to compare every element 2, 3, 5, 6, 8 till I reach target element. And the target element in the worst case may lie at the last index. So I have to compare every element of the array, and there are n elements in a typical array. While in binary search, I had to compare only two elements. I compared the middle element of the initial array, then I compared the middle element of the right half of the array, and I found my target. So from 5 comparisons, I reduced the comparisons to 2. So that's why it is counted as efficient search algorithm. Fine, so you got the basic idea of how binary search works. Now the array can be sorted in ascending order or in descending order as well. We can always perform binary search over the sorted sequence of integers. Now how can we find the middle element? What is the process to find the middle element? So to implement the binary search, we usually take two pointers. The first pointer stands at the very first element of the array. The second element stands at the last element of the array. Let's call it high. Now I find the middle element. How do I find the middle element? So in some of the implementations, we are given that the middle element is found like this, which works for some cases, but this equation does not work for all the cases. How? Because let's say since they are integer types, so for int data type in C++, we may have 2 raised to the power 31 as the largest integer value. And let's say if both low and high are comparable to this large integer, then this plus 2 raised to the power 31, this is going to exceed the integer capacity. This number cannot be stored into an integer. So in that case, we will have an overflow. So we have to take care of this. We can also understand this in another analogy. So I learned this analogy from one of the elders, and let's say we have a rod, and in this rod we have a, so let's say we have an infinite rod, and this infinite rod goes from int min to int max. Okay, so and I want to find the middle element of this rod. So let's assume that let's assume the hypothetical endpoints. Let's say it's -10, the int min is -10, and int max is +10. Obviously they are not that small numbers, but let's assume for the sake of understanding this analogy. Now if I calculate the middle element using this approach, let's say low is 7, let's say low is 5, and high is 7. So think of it as we are standing at 5, and now I have to make 7 more jumps. Fine. So if I start jumping from 5th integer and I want to make 7 jumps, then after 4 jumps I will be standing at 10th integer, because 5, 6, 7, 8, 9, 10. 2, 3, 4. Okay, after 5 jumps I will be standing at this last integer, this last value, which is the largest value which we can fit in these integers. So the largest value which I can fit is 10. The minimum value, the smallest value which I can fit is -10. So but I have 2 more jumps to make. So how would I compensate for those jumps? The jumps basically will take us, the 2 more extra jumps will take us to the other end of this range. That is, will reach here, that is 6th jump, and the 7th jump will bring us to this position. Fine. And if this is -10, if this is -10, then one extra jump will make it -9. That means this is going to give me -9. So I'm trying to meet these ends. Okay, so let's think of this as a circle. So this is int min, this is int max. So I'm trying to meet these ends. Fine. And this is going to give me -9, but it must give me 13. So that's why this formula can't be used here. So how do we avoid this? So I hope you got why we can't use this formula. Okay, so I hope you understood what I'm trying to say here, that we need to listen to our elders. Okay, so now let's use the correct formula. Let's see what is the correct formula. The correct formula would be low plus high minus low divided by 2. So even if high and low are very large, that is up to 2 raised to the power 31, if they are int, then the difference will not exceed 2 raised to the power 31. The difference will not exceed the range of that integer itself. Fine. And this is always, and this will always give me the valid middle point. Fine. So stop using this, and we'll be using this for performing our binary search. Now let's jump to the implementation part. Okay, so the implementation is simple. We have this nums array, we have this target, and what do we want to do is we want to search this target into this nums array. We are assuming that this nums array is sorted. We are already passing this sorted array so that we don't have to sort this array into our binary search function. Here we are just performing the binary search algorithm. So we initialize 2 pointers to the starting of the array, to the ending of the array, and I run the while loop. So till okay, so I run this while loop. This is the condition till L is less than equals to R. I calculate the middle point. So I calculate the middle point using this formula, and now I compare the element at the middle point. If it is equal to the target, then I return that index. Otherwise, if the element is less than the target, then that means the target element will lie in this range, that is from mid plus 1 till r. The target element will lie in this range. Otherwise, the target element will lie in this range, that is from L to mid minus 1, because the target is smaller than the element on which we are standing. Fine. And if I never encounter my target element while performing the binary search, then that means the element do not exist in the array. So in that case, I by default return -1. So that's the binary search function. And let's discuss the time and space complexity for this implementation. Okay, so we can see that we are performing comparisons. So let's say we start from an array of size n. Then in the very first iteration, I divide it into n by 2. So I have, after one iteration, the the remaining array contains n by 2 elements. After the second iteration, the array contains n raised to n divided by 2 multiplied by 2. These many elements. After third iteration, the array contains n divided by 2 raised to the power 3 elements. So according to this while loop, which says till L and R does not meet, that means when L and R are equal, that means we have exactly one element in the range, and one element means this term goes to 1. So we keep on dividing this array till this term goes to 1. That means till n divided by 2 raised to the power, let's say some k, for some k divisions of the given array, this term goes 1. We have only one element, and this is the target element. Fine. I hope you're getting where we are going, how we are deriving this result. Initially we had an array of size n. We kept on dividing the array into half till the array till the length of the array becomes 1, while this term represents length. So this is length, and this is length. This is the generic formula for length, and the length goes 1. That means n can be written like this. That means k represents the number of times we divided the array, and that also represents the number of comparisons, and hence this k is basically nothing but log of n. We know that from basic mathematics, log of n to the base 2. And what does this represents? The number of comparisons. And what do we count while search? And that's all we have to count. That counts for the time complexity, the number of comparisons before we reach the target element. So that's the time complexity. The time complexity is log of n. What is the space complexity? We can see that we are not using any extra space, the auxiliary space. We are not using any extra array or any other data structure. That's why the space complexity is constant. So in big O notation, we can write big O of log n, and the space as big O of 1. Fine. That's all. That's the binary search. Let's implement it in a editor. Okay, so this is the solution class, and let's implement the binary search function. So binary search function basically takes an array which has a length n. So let's first say we have n, and then we have array, and then we have our target element which we want to search. Now let's initialize two pointers, low to 0 and high to n minus 1. and run this while loop. Find the middle element by this formula, high minus low divided by 2. Compare the middle element in this array with the target element. If it is equals to the target, then we have got our target index, and return the mid right from here. Otherwise, if a mid is greater than target, that means the answer lies in this range, that is high must be reinitialized to mid minus 1. Otherwise, the low must be initialized to mid plus 1, and return the answer, return minus 1 at the end if we never encounter this condition. That means if we never find our target element in the array. Okay, so this is the binary search implementation. Fine, let's see. Okay, so very simple idea. Okay, so this is the very simple, this is the simplest definition of binary search, but binary search concept can be extended to problems which are more than arrays. Binary search can be extended to even those problems which do not even involve arrays. Let's see how. Okay, so the name for this concept is binary searching on monotonic functions. So we know what are monotonic functions. So we have studied that the monotonic functions are those which are either increasing or decreasing. That means if we have a function like this, that means it is just increasing, it never decreases. We can see that it never decreases, it just increases, it becomes constant, and then it just increases, it never goes down. This is a monotonic function. So if I plot another graph, let's say we have a function which just goes down like this. This is also monotonic, but because it always decreases, it is ever decreasing function. Let's take another function. Let's take this type of function. Is it monotonic? No, it is not monotonic, because here it is increasing, then it decreases, then it again increases. This is not a monotonic function. So I hope you remember the definition of monotonic functions. They are either ever increasing functions or ever decreasing functions. Fine. So we can how we can extend our concept of binary search over these functions. Now let's say we have a function fx. This is a monotonic function, or in other words, a Boolean monotonic function. So what is the meaning of a Boolean monotonic function? So if I plot the graph of a Boolean monotonic function, then let's say we have 0 and this is 1. We know that the return type of a Boolean function is either 0 or 1. That means, let's say the output of this function was 0 up to certain point, let's say x. Then suddenly it becomes 1. Now it will never go back to 0. This is a Boolean monotonic function. Let's take another example. So let's say we have a function, a Boolean monotonic function, which was 1 initially, and then it goes 0. Now it will never go back to 1. Fine. So the output can be represented like this. It is for this first graph, the output is like this: false, 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 or 0 0, false, and suddenly it becomes true. Then it just stays true, true, true. It will never go back to false. Fine. This is for this type of function. These two functions are Boolean monotonic functions. Now let's write the same for this function. It is like the output was true, 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 and then it suddenly becomes false. It becomes false. Fine. So if we encounter these type of functions in a problem, we'll have to identify them. Then we can apply binary search. How? I will show you how we can apply this. So what type of problems arise when we have this type of pattern? The problems that arise is that find the first x. So x is basically the input, f is the output. This is the output basically, and x can be some integer value. Now we are required to find the minimum x or the minimum output, the minimum input in which the function gives me true. That means the x corresponding to this output, the input corresponding to this output, or we are required to find the last input or the largest number where the function returns true. Like in this case, we are required to find the input for this output. This is a generic pattern which we observe in binary search problems. Fine. So you will understand this pattern when we will be solving problems on binary search. So this is basically an answer function, okay, and the concept can also be termed as binary search over answer. So instead of checking the hard, so what is the generic structure for implementing this function? Let's see that. Let's consider a scenario. Let's say we have n apples. Now I want to put these apples into some basket. Okay, so let's say we have a basket in which we want to put these n apples, and the size of this basket is defined by the radius of this basket. Let's say r. Greater the radius means greater the basket. The height is constant. Now I want to put these apples into this basket, and the question is, find me the minimum size or the minimum radius for the basket in which I can pack my n apples. Fine. How this is relatable to this function? Let's see that. Now observe that if I can put these n apples into a basket of radius x, then I can always put these n apples into the basket of size x plus 1. Similarly, I can put these apples into a basket of size x plus 2, and so on. But I can't put these apples into a basket of size x minus 1. I can't put these apples into a basket of size x minus 2, and so on. So these are my bad baskets. Let's call them bad. And these are my good baskets. Let's call them good. Fine. And since I wanted the smallest basket in which I can put my n apples, the answer is this x, because this is the smallest radius in which I can pack my n apples. Fine. So if I write this boolean function for these for this sizes of the baskets, I can say that no, I can't put my n apples into this basket. So this is false. False for this as well. True for this. We have true for this x. We have output true for this x plus 1. We have output true for this x plus 2, and so on. And now I want to find the x for which we get true first time. The problem reduces the same structure which I explained initially. Now I apply this algorithm, this concept into these kind of scenarios. So these kind of scenarios are repeated in contest as well as in interviews. So we have to identify that yeah, there is a monotonicity, and we can think about binary search. So think about binary search when you have to find the something like minimum integer such that this, or maximum integer such that this. Like in this, find the smallest basket such that I can put n apples into it. And these kind of scenarios are present in the problem statements. Now that's all. And corresponding to these scenarios, we have to define these predicate functions. Now that's the challenge. That's the main challenge in these type of problems, that is to get the definition of these functions. How do we satisfy those conditions for the given input x? So let me give you a generic structure for implementing these problems, for implementing this binary search algorithm for these kind of problems. So if I want to find the first true, that means I want to find the very first integer where my predicate function gives me true. Predicate function or the boolean function. This is that boolean function. I want to find the first true or this x. For that, this is the range left to right or or the search space, and here I run my while loop, usual binary search, calculate the middle element, check if that middle satisfies our given boolean function. If it satisfies, if it is true, so this is returning me true. What does that mean? It means that, let's say the middle is here. If I encounter a true, that means the first true can be this integer or it is present to the left of it. So the search space is reduced to the first half. That's why I reduce the search space to the first half. Fine, because this mid is returning true, then this mid can be the answer, or the answer can be present towards the left of this mid. So search space is reduced to left to mid included. Otherwise, if it is not the case, this is returning me false. That means obviously the answer lies from mid minus 1. The integer lies in this range from mid plus 1 till r. That's the new search space, and eventually I will have my answer stored in this low variable. So you will better understand how this low will store the answer when we will be implementing these structures, these kind of structures in the actual problem. So let's see the definition for last true. It is very similar to the first true. We have this search space, we run our while loop, we find the middle element. If this predicate function returns true for that middle element, that means the answer lies in this mid to high, because I want to find the last true, that is this one. So if I get a true, then that means the last true can be this one, or it may lie to the right of it. So the search space is reduced to right. Otherwise the search space is reduced to the left side. Why? Because if it returns false, like if I encounter some false, then obviously the true will lie towards left. So I reduce the search space to the left half, and in this fashion I will have my answer stored in this low variable. This will store the last true element. Fine. So that's the implementation of last true, and this concept you will better understand when we will be applying this on some problems. The time and space complexity stays the same for performing this binary search, while let's call it C. So what is this C? This will be the overall time complexity for first true and last true function. This is the complexity for this boolean function. So big of C multiplied by log n. This is the overall time complexity. Fine. Okay, so that's all I've got for this video. We'll better understand these concepts when we will solve more and more problems over these concepts.